Okay, this is the circuit for low pass filters. Okay, right. So this is the circuit for low pass filter. So this is the input signal. Okay, so it's a not a DC current or DC voltage. It's with respect to time the voltage is changing. Okay, and here we have a resistor. We denote that by R, and we have a capacitor, and we get our output or a filtered voltage across these two terminals. Okay, at these two nodes. Okay, so how the circuit filter out the high frequencies and only allow the low frequency? Let's see. So for that, so we consider the relation between V in and V out. So if you notice, this V in is a function of time. Okay, V out is also a function of time. So for a sinusoidal uh, input, and we will get a sinusoidal output. Okay, then what we will do is we will consider only the magnitude. Okay, so only the magnitude as capital V in, and the magnitude of the output is capital V out, which means say if I have a signal something like this, okay, then this magnitude is what V in. Okay, and at the end, if we achieve something like this, then this is what we consider as V out. Okay, so now we need to see the relation between this V in and V out for our analysis. Okay, uh, so how to get for that one more concept you need to remember, which is impedance. Okay, so impedance, it's like say you give um, oscillatory or sinusoidal voltage, and you will achieve a sinusoidal current flow as well, right? Then what is the relation between the amplitude of the voltage and the amplitude of the current? Okay, that is related through the impedance. Okay, say capital V is the amplitude of the voltage, and capital I is the amplitude of the current. Okay, then this is equal to the impedance into current. The amplitude of the voltage is the impedance into the amplitude of the current. Okay, that's what the impedance is. Okay, from Ohm's law, it looks like an Ohm's law, but even though despite of that, from Ohm's law for resistor, okay, the impedance is just R. Okay, for resistor. Okay, for resistor. Okay, what about for capacitor? For capacitor, this impedance is divided by J capacitance and omega. What is omega? See, if you're giving the voltage, okay, an oscillatory voltage, you are giving it in some frequency, right? Actually, this impedance depends on what frequency. Okay, if you give the input voltage, the voltage across that capacitor, at higher frequency it will have some impedance, and at lower frequency it will have some other impedance. Okay, so it actually depends on the frequency. Okay, what is J? J is nothing but square root of -1. It's not been called I because I guess if we put I, the electrical engineers will get confused with current. Okay, as I. So I think that's the reason it's been called as J. Okay, so now this is the impedance. So this is the relation for capacitor. Okay, Now with these things, let's do our analysis. So if we do our analysis, then we can say V out divided by the impedance of the capacitor, which is uh, or maybe I will impedance of the capacitor, which is JC omega, which is equal to V in into the total impedance, which is R plus mm, yeah, the flow of current is same. So from that, if we put that, then JC omega, no, I'm making some mistake. Yes, I'm making mistake. Okay. Uh, so V out divided by okay, V out by V in, okay, let me directly write it, which is equal to 1 by JC omega divided by R plus 1 by JC omega. Okay, so this is the relation. So this is also known as magnification factor. So it means this is the amplitude of the output voltage, and this is the amplitude of the input voltage, and the ratio is called the magnification factor. Okay, and this is a complex number. Okay, so which means we need to take a uh, absolute value for this complex number, a modulus of this complex number. So which means I need to put the modulus. Okay, and what's the modulus of this one? Okay, if we have J. So the modulus for the numerator is, even before that, what we can do is we can divide this thing by R. Okay, so that we will get it as JRC omega divided by 1 plus 1 by JRC omega. Okay, now we have to take a modulus of these two things. Okay, so what's the modulus of the numerator? The modulus of the numerator is just 1 by RC omega. Okay, and what's the modulus of a denominator? How do you calculate the magnitude or the modulus of a complex number? Okay, so you will take, so it will have a real part as well as the imaginary part, right? So the real part of, let's say, so say z is equal to x plus iy, sorry, x plus iy, then what's the modulus? It's x square minus y square. Sorry, x square plus y square. So this is the modulus. Okay. So similarly, we will take a modulus which is under square root. I forgot the square root. So which means square root of 1 plus 1 by RC omega the whole square. Omega the whole square. This is what the modulus which comes for the denominator. Okay, and this ratio, if you notice, this ratio is a function of omega. Okay, so which means the magnification factor is varying with respect to omega. Okay, now let's plot this one. Okay, let's plot this ratio, let's plot this magnification factor as a function of omega, and let's see what's happening. Okay, Okay, so this is the equation I have written. So here the W represents omega, which is given in the x-axis, and the M is the magnification factor, which is given in the y-axis. Okay, this A actually represents RC. R into C is what I have given as A. Okay, so now if you choose some R and some C, the resistor and capacitor, okay, this magnification factor is changing. Okay, so this R and choosing R and C for our required filter is something which is a design parameter. Okay, so if I lower my RC value, then I have a magnification factor uh, at low frequency which are close to 1, which means it's not filtering out anything. Okay, whatever the input at low frequency is coming as output as at low frequency. Okay, but if you look at the high frequency, okay, the magnification factor, let's say for omega is equal to 6, the magnification factor is like 0.35. What does it mean? It means in input, if there is a signal with a frequency of 6, okay, and that magnitude of that frequency has got attenuated, uh, and it's just passing only 35 percentage of it. Okay, remaining 65 percentage it has got reduced. Okay, so it's not it will not completely filter it out. Okay, but it will kind of attenuate the high frequency. That's what this RC filter does. Okay, and if I choose this RC as a higher value, then um, I could even remove uh, even smaller frequencies. Okay, and now there is one more thing. Let me go here and let me open a new slide. Okay, which is cutoff frequency. Okay, so ideally, what's the cutoff frequency? Uh, at what frequency? Let me call that as omega c. At what frequency uh, above which you chop everything and below which you allow. Okay, that's what the cutoff frequency. Okay, so in RC filters, what do we mean by cutoff frequency? The frequency the at which the magnification, or let me write it like this: the magnification factor at the cutoff frequency is 1 by root 2, or 0.707. Okay, so this is the cutoff frequency. Okay, so if somebody asks you to design an RC filter with a particular cutoff frequency, uh, they mean that above that frequency, all the signals has to be magnified, or magnified uh, below 1 by root 2. Okay, that's what they mean. Okay, so now let me show that. So here this black line actually represent, wait a second. Okay, so this, how to calculate this omega c. Okay, that's something we need to. Okay, this omega c is nothing but 1 by r into c. Okay, so you need to choose your R and C such that the 1 by RC is the cutoff frequency. Okay, so let's check that in the Desmos plot. Okay, so now I have drawn this line. Okay, this is corresponding to the cutoff frequency. So if we check here, the value, okay, the magnification factor is 0.707. Okay, now if I reduce it, okay, now the cutoff frequency is moving this direction. Okay, so once again, if you see here, it's again 1 by root 2.707. If I move further, okay, still the cutoff frequency is 0.707. Okay, so that's how you design the low pass filter. And what do you do for a high pass filter? Mm, So for high pass filter, what do we do is the following. So once again, we have the input voltage, but in the place of resistor, we will put capacitor, and in the place of capacitor, we will put resistor. Okay, and this is V in, and this is V out. Okay, this is R, sorry, this is C, and this is R. Okay, in the next video we will do the further analysis, and we'll see why this is behaving as a high pass filter. Thank you.